Welcome. Let me look at an example of the random manifold theorem we looked at already last time. So we take a three-manifold, like a three-dimensional torus. I took that here. Three-dimensional torus is obtained by taking a cube and just identify left, right, bottom, top, forward side and back side. So this room is a three torus if you make the corresponding identifications. And in the discrete you can generate this by taking the Cartesian product of three circles. Now that's not a simplicial complex anymore, but the barycentric refinement is a simplicial complex. It's relatively large already, so you see here the f vector encoded in the f function, the simplex generating function. And one of the things one can do always is go to functional versions of a theorem. We have seen that, for example, Gauss-Bonnet is a result about curvatures. You add up all curvatures, you get the Euler characteristic. But Euler characteristic is such a special value of this simplex generating function. And if a result holds for all valuations and not only for Euler characteristic, then you can naturally just formulate it using simplex generating functions. And the complexity is much lower, especially in the Dehn-Sommerville case, because in the Dehn-Sommerville case unit spheres are Dehn-Sommerville, and what you do is, if you look at these theorems, you always look at the unit sphere, so you can use recursion. So all the complexity of Dehn-Sommerville has had a hard time, right? Dehn and Sommerville developed it, and then it was forgotten for decades, and then Clay got it, and then forgotten again. It's kind of a niche thing, but it's something very well known in topology, right? You have the Euler characteristic of an odd-dimensional manifold is zero. That's one of the Dehn-Sommerville relations. And then you have the relations between the maximal simplices of the walls, the Q minus one-dimensional simplices. So this is reflected here. You see this numerically in this three torus. Now what you can do is you can define curvature, and instead of looking at curvature as a numerical thing, you can also look at curvature as a functional quantity, and that gives us a polynomial here. This is just the integral of the f generating function, and then you can compute it at -1. That gives you the curvature of the manifold. And what we have seen last time, the theorem was that you can, the expectation of a submanifold, in this case a two-manifold, two-dimensional surface in this three-dimensional space, is the Euler characteristic is 2 minus 2 times the curvature of the space. The Euler characteristic goes away because it's an odd-dimensional manifold. But, and then that's what I did this week, kind of just extend this to the functional level. So just push it up a little notch, and then you see actually that all the quantities, all the combinatorial quantities of the submanifolds are determined by the host manifold. This is very nice. And I also did kind of the computations with the whole probability space, right? If the space is relatively small, then the probability space, you know, if you have 10 elements, you have 2 to the 10 possible functions, 2 to the 10 possible submanifolds, and you can look at sum over all the polynomials which you get, and so that's a sum. That's a sum or average over all these polynomials, and this is a specific polynomial here. You see this here in this case. This is the curvature. This is the expectation. Actually, this is the result. This is the expectation generating function of a random submanifold. But I should also say all this is true for arbitrary simplicial complexes and not only for manifold. In the case of manifold, it's more interesting because it is, you know, really interesting to know, if you have a three-dimensional space, what is the, you know, on an average surface, what is the genus of an average surface. So in this case, what happens is the average Euler characteristic is negative, meaning that you have more holes. But there are spaces where this is different, where you have lots and lots of components. And for example, in a hyperbolic situation, if you have a the curvature is negative here, so you get typically something positive, and you get lots of bubbles which are not connected. And but here what you have is you have an interesting interaction structure of these random manifolds. And maybe I'll show you a picture and wrap it up. It's again a beautiful day, and I stop it for today.